we present a novel differentiable surface rendering method Cpt-Vr which shows superior performance in reconstructing the detailed structure of objects. With the closest point transform algorithm, we can address the approximate point deviation issue caused by linear interpolation. Moreover, we incorporate the view and reflection vectors to model the foreground appearance representation, making our method robust to specular highlights. In addition, we develop a simple one-point background model, enabling our method to no longer be dependent on any prior background knowledge. Existing surface rendering methods such as IDR and DMTAT assume that the local surface is planar, and thus employ linear approximation based on the SDF values to predict the point on the surface. To address this problem, we conduct the closest point transform for deviated points to enhance the geometry representation. In the appearance modeling process, existing methods such as IDR and NUS2 rely only on the view ray to capture the appearance, which cannot handle specular highlights well. Directly incorporating the reflection vector into existing surface rendering methods will lead to backpropagation errors. It is because that the reflection vector calculated based on the deviated points is inaccurate. In contrast, benefiting from our accurate point sampling on surface based on CPT, incorporating view reflection vectors in our framework can facilitate the appearance modeling of specular regions. As shown in subfigure A, we first extract the mesh via marching cubes. Then we leverage CPT to project the approximate points on the zero-level set, shown in subfigure B. Subsequently, we render the transformed mesh via a rasterizer. Specifically, we incorporate the view reflection vectors into the foreground appearance. Additionally, we employ the one-point background model to learn the background information. Finally, we integrate the foreground and background appearance to generate the rendering results. We adopt 4 supervisions to optimize networks. In this work, we model SDFnet which leverages the MLPs with a multi-resolution hash encoding. To ensure training stability, our SDFnet employs an optimization schedule that progressively incorporates the level of detail and the numerical gradients. For effective closest point transform, we directly constrain our SDFnet based on this normal consistency property. For view reflection foreground appearance modeling, our RGNet takes the 3D features, view direction, and reflection direction as input, and outputs the RGB color for the foreground. To enable the model to reconstruct objects without any background priors, we present a one-point background model composed of a MLP with an additional multi-resolution hash encoding. As shown in bottom right, we sample only one point along a view ray out of the bounding sphere. During training, we apply CPT in every iteration, whereas the marching cubes algorithm is implemented once every epoch. To enhance sampling smoothness, the grid resolution for marching cubes is randomly adjusted within a range of from -3 to 3 around a base resolution. We employ the diffras to render the transformed mesh in each view. The 3D intersection point of a view ray and a triangle is computed by barycentric coordinates. We integrate the background appearance and foreground appearance to get the rendered color per view ray. Here we show the training process. The first row shows the convergence with ground truth mask supervision. The second row shows the convergence with coarse mask supervision. The third row shows the convergence when introducing a background model without mask supervision. It can be observed that our method converges quickly even without mask supervision. We benchmark our method against the state-of-the-art methods on the DTU dataset. As denoted in the table, our method outperforms other surface rendering methods on most scans. Note that, our method achieves the lowest value in mean CD, which is lower than the second-best surface rendering method RegSDF. Since SDFnet in our method has a similar structure to it in NUS2, we also compare NUS2 and 2 rinse and volume rendering methods. Our method surpasses NUS2 on the vast majority of scan IDs. As shown in the bottom left figure, our model achieves stable convergence. Although some overlap and flipping appear in the early stages, they are barely visible by the end of the training. As shown in the bottom left figure, introducing view reflection directions brings greater benefits than introducing the 2 vectors alone. The middle right table indicates that introducing the reflection vector reduces the geometry quality of DMTAT and IDR. Conversely, our accurate points by CPT facilitate the modeling of the reflection vector, avoiding a greater backpropagation error. Thus, incorporating the reflection vector enables our model more robust against specular highlights. In addition, when utilizing the background model, introducing depth supervision greatly improves the reconstruction quality. As shown in the top right figure, our method with normal consistency loss captures more accurate structures than that with iconal loss. The bottom right table shows that training is efficient when the resolution of MC is 256, while the resolution 512 gets the lower CD. The top left figure shows the results of objects with complex backgrounds on blended MVS. Our method can effectively model the geometry of foreground objects without introducing background information, particularly the details on the surface of objects. The bottom left figure shows the results in the barn scene from tanks and temples. Our method can be adapted for reconstruction in the wild. Moreover, as shown in top right figure, we apply our method to the single image to 3D generation task. With the supervision of consistent multi-view images and normals from 0123++, our generated results appear to be of higher quality. It proves our model is capable of generating a 3D model from a single masked image. In summary, we present a novel surface rendering method Cpt-Vr. Based on the CPT algorithm, we correct the deviated points approximated by linear interpolation, enhancing the geometric accuracy. Meanwhile, benefiting from the accurate geometry representation, incorporating view reflection make our method robust to the specular highlights. Moreover, we design a background model to enable our model to handle cases with complex backgrounds without any background knowledge. Experiments on the popular 3D reconstruction datasets demonstrate the superiority of our method in surface rendering, especially for cases with complex structures and specular highlights. We hope that our designs can provide some insights for future works.